Hello, stat students. We are moving on to section 3.3, measures of position. So we're going to take what we've learned so far, and we're still looking at how does data lie? What does it look like? How far away from the mean is it? If you haven't noticed, we use X bar a lot because that mean is really telling us that's the average of the data. How does everything work around it? So when we talk about measures of position, we've got a few different things. We can talk about standard scores, percentiles, deciles, and quartiles. We won't actually talk about deciles. We'll skip those ones. We'll do percentiles and quartiles. You've probably heard about percentiles before. A lot of tests get reported that way. And quartiles we're going to need as we start talking about outliers. So standard scores, percentiles, and quartiles are used to locate the relative position of a data value in a set. So for example, if you have scored in the 88th percentile on something, that means that 88% of the data values are below it and 12% are above it. So it's the relative position. Remember, it's not raw data. It's looking at where that raw data falls, how spread out it is. So the first standard score, the first measure of position is standard score. And I call this primarily z-scores. We're going to use z-scores a lot. And so get used to using that term instead of standard score. A standard score is used to compare the position of data values on different distributions. The example that I have here in the notes that we're going to do in just a minute is, what if you scored this on a history test and this on a stats test? Which one did you do relatively better? So we can compare your score position, even though it's two different tests, two different everything. This provides a measure of how many standard deviation a data value is from the mean. So if we're talking about test scores, maybe you're 1 standard deviation above the mean. Maybe you're 0.8 standard deviations below the mean. So it gives us a relative position. If we know what X bar is, we can use our z-score to tell us what does that mean? How far away is it? Your rounding rule, there's a lot of rounding rules. I don't know if you've noticed this. Z-scores, you're always going to round to the nearest hundredth. There is a reason for that, so always 2 numbers after the decimal. As we move more into using z-scores, our tables all go to the hundredths, so we need 2 numbers after the decimal. Here's our formula. Remember, we still have to talk about samples and populations. We'll typically be using samples, but we have to still recognize in stats that population we can apply. If we've done a good sample, we can apply our statistic to our parameter. So sample z-score, the calculation is x minus x bar all over s. I'm hoping you remember what all of those things are. We'll go down the box on the side in just a second. Let's just put the population z-score formula up. It's going to look really similar. Please notice that all this sample and population stuff is relatively the same. If we're talking about populations, instead of x bar, everybody knows we're using mu's, right? Instead of s, sample standard deviation, we're using sigma. So population z-score is equal to x minus mu all over sigma. Standard deviation is standard deviation, really, when it comes down to putting it in the problem. Mean is mean, whether it's from a sample or a population. So as long as you see the pattern of that, they're really the same formula. So over on the side here, we know that x is each data value. We're only going to have one data value in this case because we're looking at your test score compared to the mean. X bar is the sample mean. Maybe you've got all these on a formula and symbol sheet. That would be really helpful. Mu is our population mean. I'm not sure why I have capital sigma in here for sum of. We don't really need that in here. I'll just do a little squiggle through that one. S, we all know, is our sample standard deviation, whereas sigma is our population standard deviation. So x, your data value minus the mean, all divided by your standard deviation. So let's do a quick example, what I was talking about before. If we're going to compare two distributions. So I have a student who took a calc test and a history test. So did a student perform better on a calc test with a score of 65? The test had a mean of 50 and a standard deviation of 10. Or did the student do better on the history test with a score of 35? The mean is 25 and the standard deviation is 5. So we've really got two problems to do. So we're going to calculate two z-scores. We're going to call these a sample because we don't really know. But by the way, on my graph here that I put in your notes, I think, remember x bar is always in the middle. So we're looking. So when I look at that calculus test, the mean is 50. And the student got a 65. So we know that they're up here somewhere. We don't know how high they are, how many standard deviations they are above the mean. If we're talking about that history test, scooch those out of there. If we're talking about that history test, the history test had a mean of 25. That was a hard test. And this student had a score of 35. It's somewhere up here. This student performed above the mean on both of those tests. But which one is relatively better? That's what we're asking when we do these problems. So we can do that by figuring out a z-score for both of those tests. So I'm going to scooch up. So let's do our calc test first. So remember our formula is x minus x bar over the standard deviation. I should have given you all of that information in the first sentence. So, or the first part of the sentence. The calc test, they had a score of 65. So that's our x. It says the mean is 50 and the standard deviation is 10. So all the information is there. Now we're just going to do a little plug and chug, put this into our formula. So z is equal to 65 minus 50 all over 10. So that's telling me that on that calc test, they were 1.5 standard deviations above the mean. If it came out a negative, they would be below the mean, right? So everything works out perfectly in math, whether you like it or not. So over here, I'm going to look at that history test. So for our history test, it says the student had a score of 35. The test had a mean of 25. And it says the standard deviation is 5. So that means when I plug into my formula, x minus x bar, 35 minus 25, it makes a difference what order you put those in because we'd have a negative otherwise, and then we would think that we scored below the mean, and we didn't. So you really do have to put your data value minus the mean all over your standard deviation 5. So what is that, 10 over 5? So that is 2 standard deviations above the mean. So if this is my mean right here in the middle, that means on the calc test, they scored 1.5 standard deviations above the mean. On the history test, they scored 2 standard deviations above the test. So the history test, they actually did better on, even though they only had a 35. That is not a very good score. However, it's better than our calc test with those calculations. So that's how we compare using z-scores. It puts everything in the same terms, how far away this value is from the mean. If you're not given the mean, remember you'll have to calculate it. All right, so those are z-scores. Our next measure of position are percentiles. So percentiles, we typically use those in education and health fields. And it's the position of an individual in a group. In education, we use it a lot in testing. In health, I think about babies. Oh, they're 54th on the height scale, 54th percentile on height, and 25th in weight. Things like that. You hear that if you ever talk to anybody who has a little baby. Percentiles divide a data set shockingly into 100 equal groups, right? Because we know 100% is a whole. The formula to figure out a percentile, we got a few extra letters in here now. P is equal to C plus, I should have put 0.5 all over N. We're going to multiply by 100 to put that as a percent. So P is equal to the percentile. C is equal to the number of data values below a specific value. This below is what trips people up most frequently. We'll do an example so you can see it, and hopefully everybody remembers that N is sample size. That will never change. So if I want to find the percentile, it says find the percentile for this data value based on this set of data. I'm going to find C, the number of data values below, and I'm going to do the math. If I want to find a data value corresponding to a percentile, I am going to do the formula C is equal to N times the percentile divided by 100. Remember, C is the number of data values below, so we'll talk about that. And last but not least, just like when we find class width in a frequency table, if C doesn't come out to a whole number, round up no matter what. So that's the second time we've done that. Always round up. So let's do an example of each of these. Notice what it's asking for. A teacher gives a 20-point test to 10 students. The scores are arranged from lowest to highest. Letter A, it says find the percentile for a score of 12. So we are finding percentile P. So P is equal to our C plus 0.5 over N. And then we're going to multiply that by 100 to turn that into a decimal, or into a percent. So let's see, for a score of 12, here's 12, right? So C, what we put in for C is the number of data values below 12. These have to be arranged in order. So our C value for this is actually 1, 2, 3, 4, 5, 6. C equals 6 because there are 6 data values less than 12. So I'm going to do my math problem. 6 plus 0.5 over, I believe my N equals 10. And multiply that by 100 to turn that into a percentile. When I do that math, I believe I end up with a 65? 6.5 over 10, yeah, 65. So this would be a 65th percentile. So 65% of the values are less than 12, 35% of the values are greater than 12. It only tells me in relationship to that set of data. Notice it doesn't really care that it's 12. It could have been 13 or 14 or 11. It would still be the 65th percentile. Letter B says find the value corresponding to the 60th percentile. I always use that C for corresponding to tell me that I'm using the C formula. C is equal to N times P over 100. So N, right, was 10. P is the percentile. So this is my percentile right here. So 10 times 60 divided by 100. Not a super hard problem to do. That should come out to a 6. 6, remember, is the number of data points below. So C is always equal to our number of data values below a specific value. So we're going to go with the 6 data values and then count to the 7th. So 1, 2, 3, 4, 5, 6. 12 corresponds to that because we have to have 6 data values below. So we came out with the same thing, right? 60%, 60th percentile was the data value 12. 12 came up to a 65th percentile. Because we have so little data, we only have 10 values, they come out close together, but this is how percentiles work. That C formula does get a little confusing. Don't forget to do the next step. go back into your data and count up. So that's kind of a big deal. All right. So last but not least, quartiles. Quartiles, we have a lot to talk about. Quartiles, you probably recognize already. We're dividing into 4 equal groups. Quarters, right? And we use Q1, Q2, and Q3 to represent our 4 quartiles. So if we were being technical, we have the 25th percentile. If you want to go back to percentiles, people usually avoid those. The 50th percentile, which is also the median or the middle, and the 75th percentile. I avoid the percentiles. I think those are the trickiest quartiles everybody gets the hang of. This actually is going back to some old school stuff if you've done quartiles, if you've done medians and things before. So to find your data values corresponding to Q1, Q2, and Q3. So you need to make sure you arrange your data from lowest to highest. It does not work otherwise. We're not finding the median if our data is all mixed up. You're going to find your median, Q2, so you're going to count from the outsides, count in. A lot of people find their own way to do this. And then what you're going to do is you're going to say, all right, here's the median that cuts my data in half. So now I'm going to find the median of the bottom half, which is Q1. And you're going to find the median of the top half, which is Q3. So if we think about that visually, it looks like this. Here's my set of data from lowest to highest. I go through and I say, all right, right here in the middle is my Q2 or my median. And then I say, all right, well then I need to take the median of this bottom half. So here's my Q1. And I'm going to take the median of the top half. That's going to be my Q3. So that's really all we're doing. There's no calculations involved except counting. And hopefully you've mastered the art of counting at this point. So let's just do maybe one I think should be sufficient, right? So it says to find the quartiles for a data set. So when I say I want to find quartiles, I am looking for Q1, Q2, and Q3. I did not put this data in order. You're welcome. So let's do that first of all. You have to do it for this. I always cross out data as I use it, because what happens if you mess up and miss one and you don't know which one you missed? 27 and 36. I have got 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces of data. 9 pieces of data. I'm just going to jot down n equals 9. We don't need to do anything with that, but just to make sure. So if I'm going to find my data values corresponding to Q1, Q2, and Q3, the first thing we find is Q2. So Q2 is always the median. I've got 9 pieces of data, so probably if I go to my middle, right, this is my 5th piece of data. I have 4 pieces below, 4 pieces above. Figure out how to do that. 18 is your Q2. If I use 18, that means that I take that completely out of my set when I find my Q1. So I'm going down here to find Q1. 18 is used. I kind of think of drawing a line right through it. It's crossed out. Notice I had a nice neat 18 in the middle. If I didn't, I'm going to have to do what I did for these guys. So I've got 2 values here in the middle, right? I've got 4 pieces of data. I'm finding the median for the Q1. So 13 to 15. So Q1 is going to be the average is equal to the average of 13 plus 15 divided by 2. So that's going to come out to a nice neat 14. So it splits it right down the middle in between those guys. If for some reason I needed to find the median of that lower end, I would not cross out the 13. So if I had 2 18s and my median was right in the middle, I don't cross them out. If I've got an odd number of data, then I cross those guys out. So up here, I'm going to find, I don't know if I confused you more with that or not, but up here I'm going to find Q3. So Q3 is the median of the top half of the data. It's going to fall right in between these 2 guys. So that means that my Q3 is going to be the average or the middle of 20 and 27. So 20 plus 27 over 2, I believe that's going to be 23.5. It's okay to have a decimal for one of our quartiles. Not a big deal, that will still work. Once you get the hang of it, it's easy. It's just the biggest question that I have is what if I had an even number of data? So let's say I had, I'm going to flip to the next page. What if I had an even number of data? I'm going to write down data. 2, 5, 6, 7, 9, 9, 10, 1, 2, 3, 4, 5, 6, 7, and 12. So I've got 8 pieces of data, right? So if I'm going to go to find Q1 or Q2, my median, 1, 2, 3, 4, my median's going to fall right here. So I'm going to find the average of 7 plus 9 divided by 2. My Q2 is going to be 8. That line does not fall on top of a number, so when I go to find my Q1, that should be a 2 there, shouldn't it? When I go to find my Q1, I'm going to include the 7. When I go to find my Q2, I'm going to include the 9. So if it falls in between 2 pieces of data, you've got an even number of data, you do not cross it out. If it falls right on top, an odd number of data like this 18, I just take that right out and find my Q1 and Q3, eliminating that 18. So that seems to be the biggest question people have. Otherwise, pretty easy. So building on that, we need to talk about the interquartile range, or the IQR. It is actually the difference between the first and the third quartiles. So that means it is Q3 minus Q1. Q3 minus Q1. Let's not do either of these examples. Let's talk about outliers, and then we can go back to the example that we did to find these things. We need the interquartile range, or the IQR, because we are going to start identifying outliers. We're not just going to say, oh, that's an extremely high or an extremely low data value when compared. We need statistics, data, calculations to show us that that is actually an outlier. So extremely high or low data values, we're going to find them mathematically. Because remember, outliers can affect your mean and your standard deviation. We talked about those earlier in the chapter, way early in the chapter. They're non-resistant. The mean really gets skewed by an extremely high or low data value. Standard deviation really gets messed up because one value that's way high above the mean or way low below the mean will mess up all of our data. Things like medians, not so affected. But if we're talking about mean and standard deviation, that's a problem. So median and IQRs are less affected because remember, IQRs are based on medians, Q1s, 2s, and 3s. Those guys are resistant. So to identify outliers, I'm working on the premise here that you have kind of wrapped your brain around Q1s, Q2s, and Q3s. So in order to find outliers, you're going to arrange your data because that's what we do. You're going to find your interquartile range, which means you're going to need to know Q1, 2, and 3. So I'm just jumping ahead that you've already done that. Once you know your IQR, you're going to multiply that by 1.5. So the IQR times 1.5, and then we use that. Here's where the calculation and the data, the support or evidence that this is an outlier comes in. So you're going to find your upper outlier boundary. You're going to take your Q3 value, your highest quartile, and add that number. This is the calculation from step 3. You're going to take your lower outlier boundary, you're going to take your Q1 and subtract that number. So if you're a visual person, my IQRs are here, right? Here's Q1, here's Q3. I'm taking the difference and then I'm adding a little bit on here. I'm subtracting that bit from here. Anything that falls beyond those values is an outlier. So if I had a super high value up there, that's going to chop that right off, and we're going to say, oh, that really extreme value is definitely an outlier. Sometimes things look like they might be outliers, and when you do the math with your IQR, you find, oh, it's actually not an outlier. So I'm going to go back to that example that we did, the practice 3. We already found the IQR, or we already found the quartiles. So let's go back and finish this. So I'm going to need to identify if I've got any outliers in that set of data. So I'm going to jump up here. So we know our Q's, right, down here. So let's find our IQR. IQR is equal to Q3 minus Q1. So I'm going to do a 23.5, subtract the 14, and that's going to be, what is that, like a 9.5 maybe? So identified our IQR. So now I'm going to start looking for outliers. So outliers, I take my IQR times 1.5. IQR 1.5. So that would be 9.5 times 1.5. If my calculations are correct, that's 14.25. Well, that doesn't tell me anything yet. IQR times 1.5 tells me how far up or down I'm willing to go. So I'm going to take my Q3 and add that value, plus 14.25. I'm going to take Q1 and subtract that value. So Q3 was 23.5. So 23.5 minus 14.25, or sorry, 23.5 plus that is going to be like 37.75. Q1 is 14. 14 minus 14.25 is a negative 0.25. So anything bigger than 37.75, which, ooh, close, I've got a 36, but not quite. Anything lower than a negative quarter, which I don't have any negative numbers at all. So that means that in this particular case, there are no outliers. If that 36 was a little bit larger, if it was a 38, I would then have an outlier. So anything larger than the Q3 plus that value, anything less than the Q1 minus that value. Right, I'm going to have you do some practicing with these. Let me know how things are going with section 3.3, and you're going to do some of this in your project as well. So this might be helpful if you're looking for outliers. Have a good day. See you next time.